Hello, everybody. My name is Sophia Wiechert from the Uncertainty Quantification Chair in Aachen, Germany. And I have prepared a poster and a talk with the title Efficient Importance Sampling via Optimal Control for Stochastic Reaction Networks. This is a joint work with my colleagues Shihab Ben Hamouda, Nadia Ben Ratchet, and Professor Raul Tampone. And we have already published an archive paper with the same title. So if you're interested, you are very welcome to have a look. Before starting, I want to drop some names and give you the central aim of this project. And this is to introduce a novel connection between importance sampling and stochastic optimal control in the setting of stochastic reaction networks. And based on this novel connection, we aim to design a computationally efficient Monte Carlo estimator for our quantity of interest. And this quantity of interest is the expected value of some observable of the stochastic reaction network at final time. This observable G can have different shapes. We could, for example, consider the projection to the ith component. This is then an estimator for the average value of the ith component at time t. Or we could think about estimating the probability that the final state is within the set B at final time. Then we use an indicator function as observable, and this is then can be used for the setting of Reactio probability estimations. And this Reactio application is actually the scenario we are targeting with our project. Stochastic reaction networks were originally introduced to model chemical reactions, especially whenever we have a small number of molecules, because in this setting, former deterministic approaches are insufficient because then the dynamics are dominated by stochastic effects. And stochastic reaction networks model the stochastic effects by Poisson random variables. There are various applications for stochastic reaction networks. They can be used to model biochemical reactions, to model epidemic processes, or to model the transcription and translation in genomics and virus kinetics. In math language, a stochastic reaction network with d species and j reactions is a continuous time Markov chain. And we can describe it by the so-called Kurtz random time change representation, which is given here in the gray box. We stack the number of molecules in a vector x, which is dependent on the time. And the number of molecules at time t can then be derived by using the initial number of molecules x0 plus a sum over all reactions j of the occurrences of the j reaction up to time t times the vector, which gives the state change per occurrence of reaction j. And this number of occurrences up to time t, here called rj, can be modeled by a unit rate Poisson process where the parameter is given by an integral over time over the so-called propensity function, aj. And the propensity function is high whenever a reaction channel fires frequently and low whenever a reaction channel is less reactive. Of course, in order to build a Monte Carlo estimator for stochastic reaction networks, we need a way to sample from a stochastic reaction network. And therefore, we have two options. We can either use a pathwise ansatz scheme. This models the exact stochastic distribution of the process, but the drawback is that this is computationally expensive, especially when one of the channels fires frequently. On the other hand side, we can use the pathwise approximate scheme, which models the dynamics only on a discrete time grid. This is computationally faster, but might introduce a bias term. In our setting, we focus on a special approximate scheme, which is the so-called Talib approximate scheme. The Talib scheme is basically just a version of a forward Euler scheme in the setting of stochastic reaction networks. This is similar to Kurtz random time change representation, with the difference that instead of using a Poisson process over an integral, we use Poisson random variables, and the parameters are given by the propensity of the current state times delta t, the length of the grid. And we also apply a projection to 0. This is this maximum term here in each of our steps. And this is to prevent negative values which are non-physical. Based on this Talib path, we can now easily build a Monte Carlo estimator by just generating m independent identically distributed Talib path, apply g, the observable to each of them, and then take the average over this g of x values. This Monte Carlo estimator comes with an arrow, and we can split the arrow into two types of error. We first have a bias term, which can be shown to be of order delta t. And then second, we have the statistical error, and the statistical error is given by a constant c alpha times the square root of the variance of g of x divided by m. And looking at the statistical error, we can already see that the statistical error increases with the high variance of g of x. And this is exactly the setting we are targeting with importance sampling. Importance sampling is a variance reduction technique. And in importance sampling, we introduce a second auxiliary random variable z with some density rho hat. And then we can reformulate our quantity of interest, which is the expected value of g of y, by using the representation as an integral, such that this expected value is the same as the expected value of some likelihood factor times g of z. And what is very important to notice here is that on the left-hand side, we are sampling from the original random variable y, whereas on the right-hand side, we are sampling from the auxiliary random variable z. But we have the same expected value. But if z is chosen wisely, we can reduce the variance. And the challenge is now to find the auxiliary random variable z, such that the variance is reduced as much as possible. Because, as we have seen on the previous slide, a small variance means a small statistical error. Therefore, we require less samples for the same accuracy, and therefore we have a lower computational effort. In our project, we are exactly targeting this challenge to find a good auxiliary random variable in the setting of stochastic reaction networks. And we're not only interested in finding a good auxiliary random variable, but we want to find the best one in a certain setting. So the best one which reduces the variance as much as possible. And of course, it's not possible to find the best auxiliary random variable beyond all possible densities. And therefore, we restrict ourselves to an importance sampling scheme. And this importance sampling scheme is based on the Talib approximate scheme, which is given here again. And you remember in the Talib scheme, the randomness comes from Poisson random variable, where the parameter is given by the propensity times delta t. And in the importance sampling scheme, we use the same randomness, but with different parameters for the Poisson random variables. So we take Poisson random variables with a parameter delta times delta t. And this so-called control parameters delta are chosen for each time step n, for each reaction j, and for each state x. The challenge is now to find this control parameters such that the variance is reduced as much as possible. And to do so, we use the notion of stochastic optimal control, and therefore we formulate the so-called value function, where the value function is the optimal second moment, given that at time n, we have a state x. We're considering here the second moment because minimizing in the setting, the variance is the same as minimizing the second moment. And this minimal second moment is then given as the minimum over the control parameters of the expected value of g squared times the so-called likelihood factor squared. Usually in stochastic optimal control, one can now find the so-called dynamic programming theorem, which gives the optimal value function and also the optimal parameters for each time step. And well, actually in this setting, we were also able to find such a theorem, which is given here. And you can see that we can find the value function starting at the final time. So this is the final time step, and then iterate backwards in time in order to derive the value function at each time n. And the right-hand side is now a smaller minimization problem, which minimizes only over the current control parameters at time n. The problem with this dynamic programming theorem is that, well, the minimization problem on the right-hand side is still not trivial. And we also have here an infinite sum, which makes it even more difficult to find this in a closed form. And therefore, we have applied a truncation of the Taylor series and a truncation of this infinite sum in order to find an approximate optimal scheme. Yeah, as you can see here in the gray box, after this truncation of the Taylor series, we have a simpler scheme, and we can derive the value function for each time step n now in a closed form. And we also can find the optimal parameters for each state x, for each reaction channel j, and for each time step n, also in a closed form, dependent on the value function. We have implemented this straightforward approach, and the computational cost of this approach is split into different costs. We first have the backward propagation, which is needed in order to find the optimal control parameters. This is the dynamic programming theorem you have just seen. And after deriving this importance sampling control parameters, we can then simulate the Talib path with this control parameters, in this case M Talib path, and this is basically the same cost as Talib with just a small additional factor. We've implemented this for one-dimensional examples and have seen a huge variance reduction. For details, please have a look at the archive or at my poster. But there's a small problem with this approach, and this is that the backward propagation scales exponentially with the dimension d. This is here at s to power d. Therefore, this approach becomes very expensive for high-dimensional stochastic reaction networks. And that's why we have developed a second approach, which overcomes discursive dimensionality. And that's the so-called learning-based approach. In this approach, we model our value function u bar by an approximate ansatz function. And this ansatz function is dependent on a set of parameters beta. At this point, it's very important to note that this set of parameters beta is way smaller than the set of control parameters delta we had before. And we can learn this parameter beta by stochastic optimization. In our case, we used an Adam optimizer. And then in each forward step, we can use the relation between the optimal control parameters and the value function, which we have seen also in the previous approach. For understanding, in the setting of rare event estimation, where the observable is given by an indicator function, we have used the following ansatz function, which is the sigmoid-shaped ansatz function, dependent on two sets of parameters, the blue ones and the red ones. The red ones can be found without learning, since they are just determined by the final condition, which is known in closed form, and the blue parameters, which give the slope, the steepness, and the shape of the slope, can be learned with stochastic optimization. As a short note, when using stochastic optimization, we also need a gradient or partial derivative, and we were able to find this in a closed form dependent on the importance sampling path. Without going in detail, we have this gradient, and therefore we were able to do the stochastic optimal control. Finally, I want to show you some simulation results. We have here a four-dimensional example, the so-called Michaelis-Menten enzyme kinetics, with a rare event observable. And in this plot, you can always see in black the optimizer steps, so the stochastic optimizer steps over time. And in dashed red, you can see as reference the values for standard Talib. Please notice these values for standard Talib are derived once for a high sample count, and that's why they are not varying over time. But this does not mean that they are constant for several runs. In this example, we have a rare event of order 10 to the power -5. And actually, in the second plot, where we plot the squared coefficient of variation, which is a scaled version of the variance, we can see that right at the beginning, we had a good guess for the initial parameters, which results in a large variance reduction. And after some steps, we were able to further reduce this variance such that we have a variance reduction of a factor of around 4 times 10 to the power 3. Yeah, if you're interested in further examples, please have a look at my poster. or in our archive to conclude my small talk, we have established a novel connection between importance sampling and stochastic optimal control in the setting of stochastic reaction networks. And based on this connection, we have derived two approaches, one working really good in low dimensions, and then a second one which does not suffer the so-called curse of dimensionality, and that is therefore suitable for approximating events in high-dimensional stochastic reaction networks. And you have seen that with this approach, we have a decent variance reduction compared to the standard Monte Carlo Talib approach. Many thanks for your attention. And if you have any questions, you can either contact me personally or write a mail to me.